All right, so suppose we're doing this same problem and we don't know about a node until we get to it, right? Think about you as Google, and you're going to search out on the World Wide Web, and you're going to do it by following links. And you don't, as I say, you don't know about a node until you've gotten to it. So we're going to start at S. And so what are the edges we know about? I know about anything connected to S, right? So of those, I'm going to take the cheapest one, right? Now I know about A. So of the edges that are coming off the blue, right? All the oranges are what comes off the blue, right? And so I take the cheapest thing, cheapest orange, right? Which could be that one. And that brings, now I know about those guys, right? And then now I can take the one, which gives me more, and I take the one, which gives me more, and then I can take it two. Everybody kind of follow this algorithm? So, all right, so in my brain, I have a right hand and a left hand. And if I figure out which one is my right hand, then I know the other one's my left hand, right? Similarly, I have memorized that there's a Prim's algorithm and a Kruskal's algorithm, and I don't think I memorized which is which, but we already knew that the other one was Kruskal's. So this algorithm is Prim's. Oh, you done when? Oh, good question. Well, they don't exist because we can't find them. Yeah, so now we're finding a minimal spanning tree of the component that we know how to reach. It's a different problem. Yeah. Same problem when it's one connected component. Amortized time. Yeah. What, the Ackermann's function? Yeah, that's amortized time. You took any sequence of operations, you take the total cost of that sequence, you divide by the number of operations, it will be at most inverse Ackermann's function of the number of objects. Right? All right. All right, so is this a greedy algorithm? No, not as defined, because the priority of the edges keep changing. Remember I said in a greedy algorithm, everything starts with the priority, you sort them. But this is what we hinted at this on Friday, right? Fixed priority is you sort the objects based on their priority, and you flip through them, right? And an adaptive priority, as you go along, you can change the priority of objects you haven't seen. And right? That's what we're doing here, right? Yeah. 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 I think I go too fast for you to write anything down, but I went, I have a number of degrees and I have never taken notes. Somehow I just, I can't listen and take notes. All right, so. All right, excellent, excellent. Some people need to be moving their hands in order to learn, right? Different people are different, yeah? Yeah. Right. Right. Exactly. All right. So what are we doing here? Greedy criteria, right? The algorithm doesn't know about any of the objects. It considers all possible objects it may ever see. It gives a real number to it. It sorts them based on, it receives them in that order, right? Decision criteria, right, is when you get the next object, you know everything you've seen in the past, you know what decision you made about them, and you make the next decision, right? So right? So here, adaptive, the Caridi criteria, you know, here it's, you know, the past, what objects you've seen in the past. And you obviously know what you did with them because you did it. And then any object you haven't seen, every possible object you haven't seen yet, you give a priority to. And then the object that's received next, here somehow out of this box, right? It tells here the algorithm, see this arrow up, the algorithm up says, I give a priority to every object I haven't seen before. And then up here gives me back the next object in my input according to that priority, right? And then I make a decision about that object, and that gives me AT, right? Everybody kind of see the flow? And that's just here all together. Here's the code. So when priorities are changing, then you use priority queue. Remember, priority queue is a bunch of objects, and you're allowed to say, give me the next one, and it gives you the guy with the best priority, either highest or lowest. And you're allowed to say, you're allowed to point in at an object and say, I'm going to change its priority, right? And remember what data structure we use for that? Heap, right? Which bubble, you change a priority, it bubbles up or down, right? So we're going to use a heap, right? So, right, here's a priority queue, right? We start with the priority queue this is very generic, right? So you start with the initial priority when you haven't seen anything, you've committed to nothing, right? As you grab the next best object from the priority queue. If the object doesn't conflict somehow with what you've committed to already, then you add it to commit, and then you have to update the priority queue. And then things bubble up and down, and then you go back up and say, give me the next thing in the priority queue, right? So in this algorithm over here, right, we start with just these edges in the priority queue, and the rest of the edges could have priority infinity if you wanted, or maybe they're not even there if you don't know about them, right? And then you pop the guy with the highest, well, the lowest priority out, right? And then as you pop it out, you commit to this, and you take A, and you find all edges connected to A, and you put them in the priority queue, right? Does that make sense? Yeah. Yeah, no, the whole point, remember, is that I'm Google at S, and I don't know things until I get to them, right? So in that regard, I'm starting with an empty priority queue, but I'm sitting at S. So anybody connected to S, I put in the priority queue, and their priority is their weight, right? And then I ask, give me the guy with the lowest priority. And it gives me this edge here. And then now I know about A. So I put into the priority queue all edges connect, all links, right? If these were pages on the, right? This page points to these pages, right? This page points to all those pages. And then this edge is cheapest. So now I go to this page and I say, who is this page pointing at? Right? And I add it in the priority queue. And you probably put breadcrumbs around so that you don't add C twice, right? Yeah. Right, everybody good with that?
Can I ask a question?
Yes, hey, this is the first question from the world during class?
Yeah. So can we, in a sense, say that the priority queue help us to achieve the greedy criteria, or we can describe the greedy algorithm with the priority queue?
Yes. Yeah. The priority queue will always hold the current priority, right?
And
And the hope is that when we get a new object in, we don't make a lot of changes to the priority queue, right? Because that's going to cost us time, right? We want to make, in this case, running time, every edge is added to the priority queue once. It's removed from the priority queue once. We never change its priority except when we add it and remove it, right? So it's fast. Yeah. Yeah. No, you'll see here, what's on the priority queue are the purple, or the colorblind, are the orange ones, right? And so which orange is cheapest? No, it's on a priority queue. It gives me the cheapest one. Cheapest one is this one. I take it. And then anybody it's connected to goes into the priority queue, right? Yeah. Everybody good with this problem? All right. I don't get a real excitement about either of them. All right. Here, this is just a slide to say what I said before class started. If you kind of look at Dijkstra's algorithm the right way, it's an adaptive greedy algorithm. You know, the D values are in a priority queue, right? You grab the D value with the smallest value, right? So it's